Good noon, everybody. I am Saidur, a third year PhD student at Rochester Institute of Technology. I'm presenting our paper titled TikTok, the Utility of Packet Timing in Website Fingerprinting Attacks. This is a joint work with Payap Srinam, Nate Matthews, Kantagiri Kongodhara, and my advisor, Matthew Wright. In our general internet activity, it is possible that potential attackers can exploit the network traffic and deduce our internet activity. The attacks are but not limited to a wireless traffic sniffer, our internet service providers, and the autonomous system. Tor is the most popular anonymous systems with almost 8 million users each day and 6,500 relays around the world. Tor can protect the user's privacy by routing the traffic within three nodes which are in between a client and the server. However, Tor is vulnerable to traffic analysis attack. One such attack is website fingerprinting attack. A website fingerprinting attacker is considered as a local passive eavesdropper. Passive means the attacker does not have the capability to modify, insert, or delete any packets. Rather, he just can observe the network traffic flow. Local means that the attacker has the ability to monitor the traffic between the client and the entry node. Several research show that a website fingerprinting attacker can de-anonymize the activity of a Tor client just by analyzing the network traffic, even though those are encrypted. To perform the website fingerprinting attack, the attacker first needs to train a machine learning or deep learning classifier with the network traffic of the sites of his interest. To collect the network traffic, the attacker acts as a Tor client and then collects the network traffic, like this example of RIT and Facebook network traffic flow. If he is training a traditional machine learning classifier such as KNN or SVM, he needs to first extract features, then train the classifier. Or if he is using a deep learning model such as CNN or LSTM, then he can just feed the raw traffic information for training. The second phase of the attack is the actual attack phase, in which an attacker is in the monitor mode to observe the network traffic of a victim. He collects the network traffic and feeds those into his trained machine learning or deep learning classifier, and the classifier then can predict or infer which site a client has visited. To evaluate the performance of a website fingerprinting attack, we use the accuracy as a closed-world metric. In the closed-world setting, the attacker trains his classifier with a set of sites of his interest. We call that as the set of monitored sites. And the assumption is that the client is visiting one of those monitored sites. We evaluate the success rate of the attack as the probability of the observed network traffic belonging to one of those monitored sites. However, this metric is not realistic as there are more than 1 billion sites in the web and a client may visit any of these sites. Which is why we also evaluate the website fingerprinting attack in open world setting. Closed world metric provides us a confidence on the classifier to perform the open world experiments. The sites which do not belong to the monitored sets are called the unmonitored sites. In this setting, we use precision and recall to measure the performance of the attack. Over the years, this attack has got a lot of attention to the research community, and they're able to get over 90% accuracy with different machine learning models. The features they primarily use are packet statistics, burst of the traffic. Burst is called the sequence of packets in a single direction. You can see the traffic flow of incoming and outgoing packets from this figure. There are certain number of packets in a particular direction, such as consider the first three outgoing packets, and we call this as the first outgoing burst. The other features that have been used across different research are the number of incoming packets, number of outgoing packets, and number of packets per second, and so on. The state-of-the-art website fingerprinting attacks are based on deep learning model. AWF attack uses a CNN model, achieving 96% accuracy in a closed-world setting. Deep fingerprinting attack uses a more advanced CNN and achieves over 98% accuracy using just the raw packet direction information. Onion sites, or formerly known as hidden services, are the special service provided by Tor to provide server anonymity. These sites can only be accessed through Tor. Previous research showed that these sites can be distinguished from regular sites with over 90% accuracy. Recent research attempted to fingerprint onion sites from middle relay, and using a Camul attack, they could achieve up to 63% accuracy in a closed world setting of 1000 sites. In this work, we are particularly interested to investigate the efficacy of packet timing to facilitate website fingerprinting attack. Coming next, we are going to talk about the extraction process of our timing-based features and the ways to represent the raw timing information and the ways to combine both the timing information along with the direction. Our timing features are based on burst, which is the key difference from the timing features from prior work. From the burst level, we extract our timing features. Among our 8 features, 3 of them are from a single burst. In this figure, we can see an example of 4 bursts and their associated timing and direction. Using the timing vector of each burst, which are marked as red boxes, we extract the median, variance, and burst length feature. Here, burst length is the difference between the timing of first packet and the last packet within a particular burst. For example, for burst 1, the timing of first packet is 0.0 and timing of the last packet is 0.2. The rest of the 5 features are from 2 consecutive bursts. To illustrate an example, IMD features, let's take the previous examples of 4 bursts again. From these timing burst sequences, we extract the median, and in the next phase, we take the difference of the median time between the current burst and the next burst. For the rest of the features, please refer to our paper for the description. Before moving forward, we want to emphasize that the value of the manually crafted features is to understand why some sites are more vulnerable than others. And as the state-of-the-art website fingerprinting attacks are based on deep learning, these manual sets of features can give us some idea of what kind of features deep learning is extracting for the classification. In addition, these feature sets can be attributed as the interpretation of the deep learning model. It can give us some ideas how we can design a more effective and efficient defenses. Coming back to the process, with the extracted features, we create a global distribution of all the features across the whole data for each feature category. Afterwards, we construct a histogram of equal size bins from the global distributions. The bin size is a tunable parameter, and the best bin size we selected is 20. We note that the width of each bin is not constant. For example, considering the median features, which represent the median time of each burst, there may be many bursts early in the trace. The range for the first bin is thus likely to be quite narrow, going from 0 up to a very small value. In contrast, the last bin is likely to have a very wide range. This notion of using a global distribution helps to keep a reference for the whole data when we process further instance by instance. After generating these equal size bins, we use the range of these bins from the global distribution to generate the final feature sets for each instances. Then we count how many features are there in a particular bin for each instance, meaning we take the length of the bin, which constructs a vector of the number of bins. Afterwards, we normalize the length vector, and then we feed those information into the classifier. To note, we do this separately for training, validation, and testing. We are also interested to investigate the performance of raw timing in a classifier, which we represent as an 1D vector of 5000 length. 5000 length is chosen following the prior work in this domain. We attempted a number of methods to combine both timing and direction information. Finally, we combined the raw timing and direction information by multiplying the timing with their associated direction, which gave us the directional timing. Directional timing is a representation of the timing information along with their associated directional sign. We also represent this directional timing as an 1D vector of 5000 length to be used in a classifier. For the experiments, we used 5 different datasets. 4 of them are from prior work, and walkie-talkie real is from our version of walkie-talkie implementation. We used deep fingerprinting model for our experiments with different datasets for different settings of the experiments. For most of the settings, we used the default DF model. However, there are some changes across different settings. For examples, for raw timing, we reduced the raw dropout rate to 0.4 and used only railway activation function. In addition, we did not use batch normalizations for this set of experiments. For all the experiments of timing features and onion sites, we used 100 epochs instead of default 30 epochs. Onion sites had only 77 instances for each class, so we wanted to make the model learn better, which is why we increased the number of epochs. For timing features, the number of timing features for each instance is 160, which is way less than the default length of direction and directional timing. So to make the model learn better, again, we increase the number of epochs to 100 from 30. Coming next, we are going to present the result of our various evaluation. We lead our evaluation with the joint information leakage analysis in WebDAV framework. X-axis represents the packet per second and time statistics from prior work and also our 8 timing features. And y-axis represents the number of bits. This set of evaluation shows that our undefended data, packet per second and time statistics leaks more information individually than that of our features. An interesting observation is that WTF pad leaks same amount of information as the undefended for packet per second statistics. However, for WTF pad, our median features leaks more information than time statistics. Among our feature sets, median feature leaks more information and followed by interburst delay for outgoing and incoming packets. Now let's look at the evaluation of our timing features. To note, we don't necessarily expect that timing features alone can provide a high enough accuracy. We use both the KFP random forest classifier and DF model for this set of experiments. DF classifier outperforms random forest classifier for both undefended and WTF pad dataset. However, random forest wins for the onion sites. The takeaway for this experiment is that timing features alone have a reasonable classification value. At this point, we know timing features render some value in terms of information leakage and classification. Now let's analyze and compare the attack performance of directional timing with only directional representation. Our experiments show that the attack performance for direction only and directional timing are identical at 98.4% for undefended dataset. However, for WTF pad, we get a performance boost of over 2% with the directional timing representation, and for the onion sites, directional timing outperforms direction by 12%. Our experimental setup for walkie-talkie datasets we collected from the implementation version of walkie-talkie is slightly different than that of the previous set of experiments, which is why we present this set of results separately. For the experimental setting details and the implementation details, please refer to the paper. We are only covering the attack performance evaluation in this presentation. We trained the model for this set of evaluation with both monitored and unmonitored traffic, as both are molded together as part of the defense. We note that if the defense works completely as intended, the combined test set should yield at most 50% accuracy, as the classifier should confuse site pairs with one another effectively. The performance of direction and directional timing are kind of identical at 73% accuracy, which is 23% higher than the theoretical maximum accuracy. An interesting observation during our experimental process is that we noticed unstable training across all the experiments and high variance of test accuracy. Walkie-talkie aims to maintain a strict molded pattern, which in reality is very difficult to attain. A simple example is that we can see a different number of instances of a single site have variable burst length. And for congestion or any other aspect of the network, the burst sequence does not always contain the same number of packets that the referenced molded burst have. And in that case, if we indeed push the dummy packets to match the referenced molded burst, walkie-talkie loses its effectiveness. And our results mirrors that kind of situations. All the previous evaluations we talked about so far are in the closed world setting. Now we talk about the more realistic open world evaluation. We performed this set of experiments for undefended and WTF pad dataset. For the undefended dataset, direction and directional timing performed relatively identically. For example, when we tune for precision, the precision is 0.991 for direction and 0.988 for directional timing. And when we tune for recall, the recall for direction is 0.985 and for directional timing it is 0.989. For WTF pad, however, we do see a distinctive performance in the precision and recall curve between the direction and directional timing. When tuned for precision, directional timing provides a slightly higher performance in the precision and 6% improvement in the recall. And when we tune for recall, we get 6% improvement in precision and slightly lower recall than the direction. We are reaching at the end of the presentation. Our last set of evaluation is on the impact of congestion in website fingerprinting attack. As we are investigating explicitly timing in this paper and congestion impacts timing, so we want to see how much it impacts to craft data website fingerprinting attack. To analyze the impact of congestion in a website fingerprinting classifier, we train our model with the network traffic from both slowest and fastest circuits. It is possible that in the attack phase, the victim's traffic is coming from the slowest circuits or the fastest circuits, which is why we set up two experimental scenarios, traffic from slowest circuit as the test set and traffic from fastest circuits as the test set. To show the difference between the mean page load time of the fastest and slowest circuits, we show an analysis of site 0 of our undefended dataset. This figure shows the distribution of the page load time across 40 circuits for site 0. X-axis represents the relative circuit order based on this shorted mean page load time, and y-axis represents the time in seconds. The mean page load time of the fastest 4 circuits ranges from 7.21 to 7.40 seconds, and for the slowest 4 circuit, the range is between 9.34 and 10.48 seconds. An interesting observation is that the variance of the mean page load time of the fastest circuits are lower than the variance than that of the slowest circuits. Our evaluation shows that the attack performance dropped across all the settings for all the data sets when we took account of the congestion. If the victim is on the slowest circuits, the attack effectiveness is relatively bad than if he is on the fastest circuit. We think this represents the analysis of the variance between the mean page load time of fastest and slowest circuits. For WTF pad traffic, directional timing outperforms for both of these settings, and for undefended data set, direction only outperforms when the test set is from the slowest circuit. For onion sites, directional timing outperforms when the test set is from the slowest circuits. In conclusion, we empirically show that timing-based features are important. Raw timing can be a powerful data representation alone. Combining timing with direction improves the attack performance, and congestion does have an impact on the attack accuracy. You can get the data and the code of this paper from this GitHub repository. We want to thank the anonymous reviewers for their valuable reviews and feedback. We also want to thank Tawang for providing details about the walkie-talkie implementation. In addition, we want to thank Mark Zuarez for providing guidelines in walkie-talkie prototype. Finally, we thank the NSF for their generous grant for this project. With this, I conclude, and if you have any questions, comments, or feedbacks, please contact us or let us know. Thank you very much. Thank you for listening to this presentation.